So good morning, everybody. So it's my pleasure to introduce Carsten Rother for our speaker today. So Carsten studied in Karlsruhe, but then went to do his PhD in Stockholm. He received it in 2003 from the Royal Institute of Technology. And after that, he went to Microsoft Research in Cambridge in the UK, where he spent 11 years. And during that time, he also produced a couple of products, which some of you might use. These were, let me see if I can get the names right. The grab cut for the Office 2010 and auto collage for putting pictures together automatically into a collage. So he was in the computer vision group there with Andrew Blake. And then in 2014, he decided to return to academia. He became a full professor at the Technical University in Dresden. But after 3 years, about 1.5 years ago, he moved to Heidelberg University, where he's a full professor and leads the Visual Learning Lab, which he's going to be talking about today. He's also a coordinating director of the Heidelberg Collaboratory for Image Processing. And he's a really productive scientist. He's got over 150 publications in the area of computer vision and machine learning. He's won many awards at various computer science conferences. He was also awarded the DAGM Olympus Prize in 2009. And so we are very glad that Carsten has come to Heidelberg at one point and is going to speak to us today. So we're looking forward to your talk.
Thank you very much for the kind introduction. A first question, who's got background in machine learning? Who knows about machine learning? Okay, a third. All right, so this will be, I will give a quite gentle introduction to machine learning as a start, like the most simple machine learning technique called supervised learning. And then we go in 3 different directions beyond this simple idea. But before that, since you also mentioned this product, so I was with Microsoft and they have to do some fancy demo. So this is what ended up in PowerPoint. I probably show this to you. We just talked about Brexit. I thought I'd have to do this is a bit of a joke with Brexit. You can do this. These probably will be even more important when there's a Brexit and maybe more difficult. Okay, anyway, so what you do here is you get a rectangle which is in the center of the image with a certain margin to the sides, and then inside the rectangle you try to automatically segment what's in there, and you can move it a bit closer, and you get this here, and then you can move it here, up here, and that's the joke you do. Okay, good. Right. So I want to introduce the Visual Learning Lab, and there I talk about the various topics we do there, and I give you a lot of different example of research projects we're doing. It will be not very technical and will show a lot of variety of projects we do. So this is currently the team we're having. There are actually 3 heads. It's me and Professor Ulrich Köthe and Akademischer Rat Bogdan Zivczynski, and they kind of lead their own sub-teams in a sense. We very closely collaborate, but they move quite independent with their research. On the research side, what we do is we do machine learning in particular, and that's mainly Uli and together with me, we're pushing explainable machine learning in the context of deep learning. And I will talk more in detail later about this. Then I would not talk much about on combinatorial optimization, graphical models, large-scale optimization. We actually still work with a team in Dresden around Jean Myers and Florian Juck at the MPI CSBD in Dresden. We work quite a lot with graphical models, also combined with deep learning for cell tracking. Then I will talk about as well today about training data generation. With these machine learning methods, it's a lot about data. How do you get data? And this is and some of the works we do in this respect. On the application side, we do a lot on scene understanding. That's more standard computer vision. And what's new is what we're pushing a lot, and what's also very prominent in the talk here, is to use machine learning, explainable machine learning, and other techniques for natural science. And that's what we are very interested in Heidelberg. And this is like a great platform here to dive into all sorts of natural science and life science. We currently have ongoing collaboration with astrophysics and medicine, which I will talk about today. Then, as I said, biology we also had in the past, and we just had, for instance, Bogdan Sachitsky also had with EMBL, just got a grant accepted on biology and optimization and machine learning. Then I'm actually professor in environmental physics. I'm the successor of Bernd Jene. So we also talk with people from the IWR on, for instance, environmental physics and Department of Physics, how to do some of the techniques we use for environmental physics. Okay, so let's start with very simple machine learning. So one of the oldest tasks in computer vision machine learning has been to recognize what's in the image, and there are 1,000 classes, and you got a certain number of training and test images, and I come to that in a second, and you have to recognize what class it is. Now, networks before 2012 have been not using at all neural networks. Since then, neural networks became very prominent. So before, the error rates were for this particular class to say what's in the image. You can say for every image you can give 5 guesses out of the 1,000, and if you're wrong, then that's the error here. So error rates were around 27%. It went slowly down, and this was the introduction to neural networks, where there was a big jump in reduced error rate, and since then networks get deeper and deeper and better, and we're currently, that's 2018 probably, now it's like 2019 we are at 1.8%, something like this. I didn't get the exact number, but this is currently where we stand. And actually humans, it's quite difficult also not easy for humans to do this. If you go back, for instance, there are 1,000 different classes, and some of these beetles, there are different type of beetles, are hard to recognize. So also humans have an error of 5%. So now these are neural networks, and what are neural networks? In a nutshell, what they do is they take an image. The most simple form we can think about taking every pixel and lay it out here in the input, but I will come to a more elegant form, a more form which works better for images. But basically you get the input signal, then you go through different layers in the network to come to an output neuron. This output neuron could, for instance, be if it's just binary classification, like between 0 and 1, 0 could be flower and 1 could be cat, for instance, just as an example. I come to more realistic with images in a second. So this network, what it's doing is there are linear combination between the weights and the input vector, and there's a non-linearity in here. Because otherwise, if it's all linear, you could fold it into one layer. There's a non-linearity in here, and then you propagate it further. There's a non-linearity in here, and you propagate it further. Okay, so we always have 2 stages. We have the training time and the test time. So at test time, you simply put your input into the network, and you get your output. At training time, we have, this is the supervised learning, which is the most simple form. We have the input images with the corresponding labels. So we know that this is car, or we know that this is flower. Okay, then what we do, like this is the most simple form of writing it, the error function, also called loss function, is a sum of all training examples here, where you get the prediction of the network, and the true output, it should be minimized, the distance, like this is a squared loss here. Okay, so for images you have another network which works better because there are less parameters, and you can then make it more deep. So for images you have convolution. So you have a filter here which is a convolution over the image, and it's the same filter at all of these positions. And then you get the output of many different filters, and this is then the filter bank here. Then you have to this filter bank, you apply another filter bank, and you get even deeper filter bank. Additionally, these filters naturally can also, there are some forms of max pooling or other operations to make these images in a sense smaller and smaller. In essence, in the end, they're so small that you make it a vector and then a fully connected network to get the output. And so these networks are really these top performing networks. Okay, so this is the most simple form. I now have 3 different questions which I want to dive into with this most simple form of machine learning. The first question, I want to show you one project where we're aiming at adding prior knowledge to the network. This is maybe a topic actually together with Ulrich Köthe and Bogdan Sevchinski, we may actually make this a bigger topic. There's huge amount of prior knowledge, and I will just show one example where you know the forward process, but there are all sorts of prior knowledge, even from we talk to some legal people who've got some completely different forms of prior knowledge, how to incorporate that in the network. That's a very interesting question. Second question is, can you explain me what the network is doing internally? And I will explore a bit on this, what we're currently doing. And the last question is, how do you get labels of training images? And this is certainly very important when you want to stay in the supervised domain, which is currently the best performing. This is the most simple form, and this gives you the best results. Okay, so let's start with the first one, how to add prior knowledge to my network. We have actually various interesting projects also when there is like sampling and so on involved, but I didn't want to spend the time to only dive into this topic too deep. So this is a work we did now 1.5 years ago, where you have the hidden parameters y, which is the true output which you want, and then you've got measurements x. And now what you want, you also know the forward process. In this time, it's like a known forward process. And I come with the next topic, I come to unknown forward processes. But in this case, we know the forward process, we can actually write it down. This is the convolution kernel K, and convolve with the image and adding noise, and then you get these images here. So now the question is, how do you invert this process? You can either take a classical algorithm, which I will show in a second, or you take a pure neural network. You can also take just one CNN to convolve it to get this image back, or you take a combination, which we did in this particular work. So if you take, for instance, a Wiener filter, which we are building on, which is not a bad way to convert it, it gives you, in the simple form, it gives you these ringing artifacts here. So this is okay, the inversion, but it has ringing artifacts. This is certainly an ill-posed problem because the high frequency are lost here. So how do you reconstruct them? That's the main question. And this is a feasible solution, but it's not a nice-looking solution. So now if we have machine learning in there, it regularizes the solution and says, well, I want to have images here which look nice. Okay, so this is what the machine learning learns. And in this particular work, we happen to do this, iterative refinement with a neural network called so the CNN, the convolutional neural network involved in here. So these red parts come from the neural network parameters, and they are added into an iterative form of the Wiener filter. And in this way, you get this nice looking result here, where basically the network has to learn to say, well, so before this is just, and especially also like looking at the whole image, this doesn't look natural. So this looks more natural. Okay, so this is what the neural network learns. When it has seen a lot of images here at the training stage, how to invert it, then it learns this regularization. Okay, so this is just to show you that we can have simple forward processes where we can combine it with neural networks to make them better. Okay, so here's an example. This is actually without the forward process, but it's a very nice and low-hanging fruit. People from Gene Meyer's team in Dresden have done this work. And so that's what I'm also looking in general with when I talk to natural scientists, when tries to look at low-hanging fruits. They're often sometimes in a particular community which is not, with machine learning, you can do it in a much better way. So here's one example. You've got the fly wing and you've got the living fly wing with low exposure microscopy. You get a lot of noisy images. If you were to kill the fly, and you've got a high exposure, then you get such image. But obviously, when you take obviously you want to have the living fly, because then you can take even movies, right, of this fly wing during development. So now it's a very simple thing, but for neural networks, you can take these ones here as training data. So this is the input to the network, and this is the output to the network. And you can generate with low and high exposures a lot of training pairs, and you train a neural network, and this is the output of a neural network when the input was this image here. Okay, and so obviously there are small differences, but biologists like to look at these images more than these noisy images. Again, the network has learned from a lot of training pairs how it should look like. Okay, let me come to the second question, and this is the main part of the talk. Can you explain me what the network is doing? Here I want to give three different answers. The last one is gray because we are still in progress doing these works, and but these are things we currently discuss internally, and they're ongoing. So what I will mainly talk about is uncertain outputs. You want from the network not one output, but a whole distribution of outputs, and I show you how we're doing this at the moment. Then I talk about feature visualization. You try to look into the networks and see what the features look like and how you can understand them. And then we currently go in our research further, where we look at concept discovery. So is there, for instance, the concept? You can, for instance, think about birds. They have, for instance, a beak, or they have feathers, and you can ask the question: is the concept of beak in there, or is the concept of feathers in there? So rather high-level concept. We currently do something on concept discovery. Causality, we start to talk to people doing drug design and some other fields. Genetics, we look at causality questions and other aspects here. Okay. So this project is an ongoing project with with our lab, where Ulrich Köth is the main PI, and DKFZ, Lena Meyer-Hein, and the Star Formation Group around Ralph Klessen. Okay, so I already talked about the deconvolution problem, where we have the noisy measurement and you have the true image, and this is the forward process. Where you go from this image here to the noisy one. Very often we don't know the forward process, but we can get a lot of pairs of this forward process. But we don't know. There's very complex these simulations, and they will be hard, as I showed before, to directly include them in the neural network. Okay, so we take this one here as a black box, and now you can invert it. And the standard approach is you have a lot of training pairs for the X and the Y, and you then construct a neural network, and you simply train the network with a certain error function. We call it supervised loss, because we know exactly these two pairs, and we train that with this input you should get as close as possible to these hidden parameters here with this loss function. Okay, so what's the problem with this? They are quite often, and this is the main point of the work, ambiguous forward processes. So let's look here. We've got certain parameters. For instance, we've got these 2 points which map to the same measurement, right? Now, this is a problem when you train a neural network. So the first thing is that when you train a network, it gives you one output. Okay, so for this measurement, which output should it give? Should it give this one? Should it give this one, or intermediate one? Right? That's the question. And the next thing is you would ideally like to have the full distribution of possible solutions, and with a certain measurement. And there are various approaches with Bayesian neural networks and dropout and so on. But what they all assume is a loss function on this side here. So you always try to make your inverse that the output of this should be as close as the truth. So you have a loss function on this one here. And I'll show you in a second that in our approach you don't need this. We will have a loss function on this side and not on this side. Okay, there are networks, and I explain them in a second, which are so-called invertible neural networks, where you've got a one-to-one mapping from the parameters to the measurement. There's every parameter has got one measurement, okay? And these are constructed networks. And now what we can do with these constructed networks, we actually do also a big project at the moment to look between constructed network and softly enforcing it and so on. We look at a lot of different network architectures, but this is the most simple form, which I will explain here. So what happens now is that we have, because of this unique mapping, we have one parameter here mapping to one measurement, but additionally we introduce a latent space. So this is the kind of the measurement space together with the latent space, and this is the parameter space. So because it's unique, there's a one-to-one mapping. If you draw in this space, you draw 2 points here, right? And these ones have to you must get uniquely back to this point. That means if this point here maps to this and this point maps to this, they must map to different places in the latent space. So the latent space distinguishes between the different bumps here, between the different modes of the distribution. So here you encode all of these ambiguities of the distribution, and here you encode the making the forward process as correct as possible. I will not go into much of the theory here, but we can actually prove that if you train, so the supervised loss is only on the forward process. So what we train is the forward process to make this as good as possible. And if you actually manage to get a zero loss here, the error function, the error is zero, then we get the true distribution out on this end here. So what we do, and I'll show this in a second, we actually sample in the latent space here, and by sampling the latent space, we get all of the whole distribution out. Just to go one level deeper, so during training stage, we have hidden parameters. We have a learned forward process. We try to replicate the measurements with the supervised loss. And we have the latent variables. Now, there are two, they're called unsupervised losses because we don't need training images. So what this is doing, it's actually forming this one into a distribution, in our case a Gaussian, high-dimensional Gaussian, for which we can sample from. And also make sure that these two here are conditional, or the output and the P of X and P of Z are conditional, they're conditional independent between these two. And also there's a small unsupervised loss here, which is just for regularization to make sure that this distributions match of the parameters of the true parameters, and if you invert it on the parameters here of the output in the inverse process. So these ones are regularization, unsupervised losses, and this one is the main loss when you train the forward process. So during test time, what we do is we sample from the latent space, then we take a measurement, and then we get out the distribution of the hidden parameters. Okay, so let's want to just show you a glimpse of the network, how they look like. So this is one of the networks we are currently exploring, which is by construction invertible. So you get an input here in the forward process, you get an input and output. You split internally the vector, and then you get, and then you have got arbitrary, S and T arbitrary neural networks, convolutional neural networks, for instance, and then there were these operations added together. And by construction, and I do that in my class, it's like it takes 2 minutes to see that you, like by construction, can invert them. You go from the output here, the other direction to the input, by just making a minus here and making the multiplication, a division, and the plus and minus, and then you go the other way around. And the beauty here is that you don't have to invert these networks internally. You just have to, by this construction around it, you can invert it. Okay, so here's an example from robotic. It's a simple example where we have two-dimensional measurement. You want to say that this robotic arm should grasp exactly at this position here. So there are three parameters, which is the position of the arm here, up and down, the angles, so one angle here, and the position of the arm, and you should grasp it here. Now what we want is, we want to make a certain measurement, X. Now we want to sample from the latent space, and we want to get all configurations of the arm, which samples here at this endpoint. And this is the latent space where you can now move through. So this is always the green point. I will play a video in a second, moves around, and this samples from the latent space. And every sample is a different configuration. So now I play here. So it's actually Gaussian. So this is the most likely position here. And the most likely there's a small prior on that the arm shouldn't move so much. Okay, I'll probably play again. Okay. So this one, as I said, is like this anchor here should not move so much up. So this is the price, the most likely configuration. And then you can move to different configurations. Okay. So now you can also change the conditioning, and then you get, this is the most likely configuration, get a lot of different arms. This is now changing the measurement X, and you get a lot of configuration, which are the most likely configurations. Okay, so I will now show some experiments and results on comparison on the kinematic chain example. I talk about medical multispectral tissue imaging, then what we've done with the astronomy, and a new project we just started, which is on guided image generation, also with these invertible networks. In general, what we're interested when we talk to natural science is to say they're interested in, can I trust my output? This is, for instance, for the astronomy, very important for them. Another question they're often asking is, can I change my measurement device to get a more unique output? This is basically experimental design. So this is currently what currently in submission, a project with the medical team, where you change, where we try to have the a measurement device which makes this output as unique as possible, so you don't have a bimodal distribution. Can I design a cheaper measurement device with the same quality output? You kind of say, give me similar looking distributions. They're a bit of ambiguous, but it's okay, but give me a cheap measurement device. Or can I simplify my simulation and still get the same result? Because less parameters are faster simulation. I will also show that in a second. Okay, so for instance, on this toy example of the robotic arm, we have various, we can do various competitors. This is the absolute baseline, which is called approximate Bayesian computation, which basically only accept arm configuration really end up to this point, and you get kind of called internal error, which I'll not talk about now. It's called calibration error. It's really zero. So this is a perfect result, but it's completely infeasible if you go beyond 4 parameters, basically. It's called, that's the gold standard. So now what we get is with the INN, these are all arm configurations where they end up at the same point here, the same target, and these are all visualized in a, with this kind of fainted lines. And you see it like looks very similar to the true distribution. And this calibration error basically measures how these distributions match, and it's very close to zero. This one is currently the closest competitor in literature, which is called conditional variational autoencoder, and it gets the shape of the distributions not as good. This is also an error of the 97.5% points when you resimulate, they end up at the same position, and it's also like a bigger surface here. Okay, so with the medical team, what we've been doing is we do simulations of tissue. So you simulate tissue of different perfusion and different thickness and scattering. And they have, for instance, did 3 different layers of skin tissue. Then when they're simulated, there are certain, like when there's light, so it's an active illumination, light comes in here and scatters back. Now from the spectral response of the surface, you take certain measurement at some positions here. Okay, and this is basically what we get. So we know the forward process, and that's a very complicated Monte Carlo simulation, what they do, and they get measurements out. And in their previous work, they've exactly trained a neural network to invert this and get out these original parameters, and now they want to know, is it unique? The particular thing they want to know, and this is really important for the operations theater, and the first tests are actually done with their current system in the operation theater, is you put clamps, it's a bit hard to see here, but on this image you put clamps here, and now you want to see what's the oxygen level around these clamps, because that really decides where to place the cut and or when to place the cut. So they want to know the oxygen level, and this is, for instance, one of the uncertainties we get out with our oxygen level estimation. Now the main thing what they wanted to see is it unique, the answer, and what is our how good is our simulation. So what we see is on the oxygen level with our approach, we see, and this is the close to the true output, we see that the oxygen level can be very uniquely estimated. So the purple distribution here is the distribution of all parameters of this all possible numbers for this oxygen level, and you see it's a very sharp peak. The gray in the background is the prior. So without the forward process, this is the prior over all possible oxygen level. And you see that with the measurement, you can really get out, okay, this is the oxygen level. The other methods are also pretty good. Ours is even more sharp. Now, nicely, what you see, there are no multimodal distributions, so it's all relatively unique, all of these other parameters. But these parameters here are basically the same as the prior. So what we see, they're not worth to simulate. When they get the distribution out, they are the same as the original prior. So the gray curve is just behind this purple curve. And so you didn't get anything by taking the measurement, you didn't get any extra information. And they actually then, when we talked to them, they said, yeah, that makes a lot of sense because this one, D is something, D and G are very deep down in the tissue. And they already thought that this may not affect their final result much. You also see strong correlation. So this correlation matrix between different parameters, and you see certain parameters are highly correlated, others are less correlated. Okay, so with the astrophysics, we have physical parameters of star clusters. The forward process is complicated. We are not interested in the details of this. And we so-called observed like spectral line ratios. This is kind of measurements they give us. And here it's interesting because we get bimodal distributions. For instance, on the parameter of cloud density, with the given measurements, we say, well, there are two possible solutions for it. The slightly more likely solution is that you have this form of like this amount of cloud density, or this one. This one also gives you a solution which is nearly as likely as this one here. And again, you can look at correlation matrix and you see which parameters here are more correlated, which ones are less correlated. So they're very excited and they want to, with us, with this invertible neural networks, build a tool for astrophysics to analyze all of their data and make this really like a full-blown software tool for astrophysics. Okay, so this is the most recent work we're doing. It's actually on image generation. You can also use this network for. Now, what is the forward process is something different. So you've got an image, let's say here, like this called MNIST in our community, MNIST image, and you plug it in, and the measurement is only which number is it, between 0 and 9. And now the latent space is the size of the whole image, and you can encode, you can actually sample from this latent space and get different images back here. Now what's interesting is this latent space here there are certain meaningful positions in the latent space. So for instance, you can change the conditioning here, you can change the number, and you say, okay, this one, if I sample a certain point set in latent space, I always get numbers which are slanted. Some other latent space here is tidy image writing, others is faint image writing or thick image writing. So it's kind of like what we do a lot when we do such embeddings is we try to find representations which are as meaningful as possible. This is now jumping a bit out of this particular project, but people are, just to show you what other people are doing, there's, for instance, people have looked at this latent space and tried to find directions in the latent space where they have got also, where you do sensible changes to the image. This is, for instance, one of the projects where they found H-axis. Probably you can also invert it if you want the other way around, or a beard axis where you add add a beard to the image. So this is currently quite hot in our community to find representations, to do representation learning which are as meaningful as possible. And particularly, I think for natural science, this is interesting because you have interesting latent representation, latent spaces that you can understand them and may get more insight on your particular task. Okay, so the next one is feature visualization, the next topic on this explainable machine learning. So this is not our work, but it's like just to show you what's currently ongoing in the community. Okay, so here is again this convolution neural network of having an image and giving out what class it is of these particular images. And now it's interesting question you can ask is to say, give me a neuron at a certain depth in this convolution neural network and generate images which excites this neuron as much as possible. And if you take a neuron from the first layer, then basically images which excite this neuron most are images which have got bars or are kind of blobs with different orientation, like two-sided blobs or a single blob, different orientation. Now, the more deeper you go into the layer, into the network, you see certain parts. These are, for instance, roundish shapes, or these ones are like, yeah, some blurry shapes here, which the networks start to respond. And now the deeper you go, for instance, this one here is actually firing with wheels of cars. Now you get more towards the actual task here. And now you start to see, for instance, it fires on certain parts of the network or here on texture, and then you get very deep in. You get actually features which neurons which really fires for dog faces, or I don't know, clocks from the side and so on. Okay, so this is very interesting like there have been various tools developed. This is a bit like from 2014, older work, but there have been various tools developed in the recent years how to analyze these networks. Just a bit of on the fun side as well, you can actually go a step further and generate whole images, and I'll show a video in a second, where you increase the probability, for instance, of animals, like for birds and dogs or general animals. And so how would these networks look like? So this is now playing a video through a shopping scene where the network generates a new video, and it says I want to see, give me an image so that I see more dogs or more animals in. And then, for instance, what you see is like when the child moves, that, like, for instance, here like a dog face, so like human face and dog faces are not that dissimilar. So it's kind of looks a bit scary, but it's interesting when you do such things. You suddenly may get an inspiration for your own research. Okay, so let's come to the last question: is how do I get the labels of training images? As we've just seen, it's like the more labels you have, the better you get. But where do you get these labels from? Certainly for tasks like classifications, it's not so difficult. But for other tasks, like for the images, like for deconvolution, it may be harder to get these pairs. So I will show 3 different projects, in particular the simulation, what we currently do on this particular question. Okay, so this is a project we've been doing with biologists, where we get this flywing in, and we want to get really 0-1 labeling of each individual cell here, and all of the membranes are 0. And what we did here is a crowdsourcing approach, which is relatively popular. You also have some companies providing this, but we actually we use the company which gives us the labels, but then we didn't want to pay the amount of money. It depends on how much money you pay, the quality of labelings you get back. Here we said, we only pay you half of the amount, and we get all of the labelings back from people. So some people really carefully, so these people then get money for the labeling, or they get food or something like this, right? That like depends on where on the world it is. So these ones are sent out to everywhere to the crowd, and they get labeling back. So some people really care about and make even every membrane draw it with 2 lines. Some others make it relatively careful. Some others ignore the task and hope to get through and still get money. Some others were started really excited, but then get bored when they saw the rest of the image. Anyway, so this is the output of our system, and we use all of this in a robust way to merge it to get such an output. Okay, so simulation is what we currently push quite hard in our team. Particular, this is part of the HCE, which I'm the director of. We have got various projects here, and especially this collaboration with Bosch, which are very interested in autonomous driving. And so one thing is like how to get labeled for like driving scenarios is virtual reality. So you can get you simulate the whole world. And you get, and in this way, obviously, because you simulate it, you know exactly for every pixel, is it car, is it street, or is it sky? You can generate a lot of data, but it's really hard to get high quality. So I say here medium quality. The cars are okayish, easier to do, but especially trees and so on are really difficult to simulate all of it well. Another thing what they're very particularly interested in is dangerous scenarios. They want to have these critical scenarios where there's a person direct in front of the car, which is possible to do in this virtual reality, but in real world really difficult. So now what we currently do is mixed reality. We say, well, we have real imaginary, and we use that, and we just add cars in as realistic way as possible, and I come to two different solutions, a pure graphic solution and a neural network solution to generate such images here. So it's easier to get higher quality because you take the true backgrounds. Okay, so the first project we did was on pure rendering. So we do rendering and post-processing, and I come to this post-processing in a second exactly, that this is really important to do all the fine details right for the network. And so we simply have the background and we have the object, and we can render it in the image, and we can get for free the labeling because basically just placing this mask here on the background. Okay, and what's quite nice, we can considerably improve the state of the art. So this is state of the art this is precision, average precision for recognizing these cars, so the higher the better. And this is when you have real training images. This is with virtual images. The quality is not so good, only virtual images, like these ones here. You get your slide, you've got many, many more. I think there are 5,000, where here's only 300, but the quality is not as good. So what we get when we do augmented reality, these are basically real scenes and a lot of cars additionally augmented. We get a big boost in performance. Interestingly, when you combine it with virtual, you even get another improvement. This, for me, tells me that it's not realistic, these synthetic renderings, but it's just different scenarios. And it's very important in our community to look at this generalization performance, and the more data, even less quality, but different data is important to have. Okay, so here we did some checks to see what really gives you the good results. Certainly the background is important. When you've got synthetic backgrounds of scenes of cities, you get 47% accuracy. It's close to 49 with the real backgrounds. But if you have crap backgrounds or black backgrounds, it really drops in performance. Another thing which is really important with these networks is the fine tuning of the visual quality. So this one here for you looks. So these are both rendered cars. I think the background this is a real car. These are rendered. And this one is without post-processing, and this is with post-processing. This basically post-processing makes the foreground as close as possible in terms of all sorts of image statistics, blur, color shift, and so on with the background, and you get a huge gain in performance. So if you don't do this, it's basically data is useless because you're in the range of the real data. So all of these details matter a lot for the networks, which we're currently actually having a project with NVIDIA ongoing, also like an internship of my students, which I'm also involved in, to really understand what these networks do internally and see what is important to get right here in order to get this boost in performance. The latest thing we do is to overcome a problem that typically with the background you don't have all the information. You only have, for instance, you don't have all the lighting information, no 3D. So we currently replace this whole graphics with a convolution neural network to give you to render cars completely, even with shadow and everything. And now it's interesting because you have two losses. One loss, one error function, you want to make it as close as possible to the rendered image. And another is called a gun loss, which is very popular in our community at the moment, which is another network. So there are two networks which train simultaneously. and you want to make this one as realistic as possible. And so what it means is that this network's the only task is to distinguish between real images. The network doesn't know if it's a real or faked image, and it has to say, is it real or faked? So it has to distinguish as well as possible between these two classes without knowing for the image where it comes from. And the goal of this network is to fool this network as good as possible. So this network has to generate as realistic images so that this network really has 50% chance of being right. So they play against each other. It's actually a difficult optimization problem because it's a min-max optimization problem. The kind of loss basically internally like maximized, and this is minimized. So it's like a difficult optimization, as even Nash equilibrium and so on plays in here. It's a hard optimization problem. Nevertheless, people succeed with it. So first of all, this is like without this gun realism, and this is then with the gun, and you see these cars blend much better into the background. And you also get, sorry, these ones are swapped, should be 38 here, 37 here. There's you get also 1% improvement. So just to show you, which is currently popular in our community, is you don't even, if you don't throw in like these models and background, you can throw in random noise, and you can take any distribution, for instance here celebrities, and you want to have a generator here, this generator here, which generates celebrities, and this network, the GAN network, has to distinguish between celebrities and generated images, and from random noise. And these networks are getting better and better, and I will show in a video in a second what they currently can achieve. This is again this 2 network training. So these are all faked celebrities from a pool of real celebrities. And the main problem with this one is one of the main things, you start to see here some blurry artifacts. So this is a bit cherry-picked, I think, the results. Look, I mean, yeah, here this doesn't look so realistic. But they get every half year you get, or every month you get better and better results and so on. And you can use this for a lot of natural science. Like this is a general way of basically sampling from a distribution when you only have a lot of examples of it. Okay. Just to summarize the last project very briefly, it's not about generating labels, but circumvent the whole problem of generating labels. We've got an ongoing project called Co-Segmentation. The idea here is, so for instance, when you want to do semantic segmentation of this image, you want to get out for every pixel which class it is, but you only have trained data for 20 classes, like these classes here. Okay, now what we have a project with, together with Hanover on finding construction sites. So we have got these images here of our bicycle app. So we cycle around Heidelberg and Hanover and want to build automatic apps for bicycles. And so I want to say, segment me all the construction sites. And how do I do this? Construction site is not in the list. So what we did was we simply went on the web and took a lot of images of construction site to give me examples of construction site. And then we train a network, and I'll show how the network looks in a second, to give us, to segment automatically the common images, called co-segmentation, the common objects between all these images. And the common thing is this construction site. So just to show you how you do such a network, it's trained on supervised, again on these classes, and in a kind of Siamese network where you've got the images going through a coder in a feature space. In the feature space, you do correlation between these images. So you correlate this one with this one. And there's actually a person here in the background. It's a bit hard to see, but it's laying there, the person. And so it finds person, features person, and this one is highlighting person, isn't common between the two, is person. And here again person, and this decoder then makes the segmentation. And then this you get out, you get the common objects between these out. Okay, and here are some results. These are all classes which are objects which are not part of these classes, and you get them quite well segmented. Okay, so that concludes my talk. I hope I'm still roughly in time. And I went through these 3 questions with starting from supervised learning to more exotic forms of learning. Thank you very much.
Okay, thank you, Carsten. That was really great. So are there questions?
So, thanks for the talk. So one question that occurred to me that is, how do you know that you have a continuous ordered latent space? Something like that, that is continuous for all the samples and not like drops for one of these input samples that you input in the network.
So the latent space Z should be continuous. I mean, quite often what we look at is that it's well covered, so that the certain parts of latent space are not completely empty. And so, yeah, I mean, we look at these invertible neural networks to, for instance, variational autoencoder and others, and they often have the problem of not laying out the latent space well. And we are kind of with the INN, it implicitly tries to use the whole space of variables, of Z variables, because otherwise it would lose power, this representation power. But actually, the latest thing we're doing is maximum likelihood learning. It's not as a different form of learning here. And this, yeah, I mean, we've seen that it uses the latent space well. If it's intuitive, the latent space, this is the open question. It can be, that doesn't have to be.
Linear scaling, something like that for the latent space.
Yes, yes. I mean, you can certainly always move linearly in the latent space, but it should move along sensible dimensions, and this is not clear. But for most of it, I mean, it's certainly like a sensible solution is a compact one, but there could be other solutions that are also compact, which are not sensible. But I mean, to draw figures to say, okay, which figure it is and like faint and so on, different styles, it makes sense to distinguish between them. But the network could do something else as well. You don't know what the network is doing. It could converge to a different solution. But what we've seen, and others as well, it's quite often very sensible latent spaces. Mm-hmm.
Well, maybe this is very... Okay. I don't hear myself anyway. Okay, good. Well, when I look at this image, when you do convolution, you definitely imply certain size of the convolution mask, right? And the problem in biomedical imaging is that sometimes you have, let's say, update of your cameras, of your screening sensors, and you go into another resolution. And certainly features exist on a certain scale. Right, there is certain limitation with respect to the size of this convolution windows. One tries to keep it as small as possible. Let's say 64 by 64 is such common convolution window. How would you suggest to approach in such case the problem of finding appropriate scale for pooling the features for neuronal networks?
Mm-hmm, mm-hmm. I mean, certainly what everybody is doing, but that's not solving your problem, is, I mean, to make sure that it's the same resolution, right? When you squeeze it into the same resolution.
Finding
right?
Appropriate scale for...
Exactly. Finding appropriate scale. Yeah, at top of my head, I don't know. We have not done this particular question, but I don't know papers which have been doing this. I mean, first solution is certainly you train it for different scales, right? So that you have it right, but then you would like to interpolate, or then you have also like a discrete decision which scale it is and so on, right? But I mean, I can think further on the top of my head, but I don't know. The right papers at the moment to which tackles this, but certainly it's like people have tackled it, this particular problem.
Okay.
Mm-hmm. But it's an interesting, I mean, it's an interesting problem, certainly. Yeah.
I'm wondering how you did the MNIST classification task or any other classification, because in order to minimize some cross entropy, you would need a softmax layer, and it's not really invertible.
This Yeah. No, the softmax is invertible. I mean, you can. I think that should be. I mean, that's like a new project the student did, but he. I think that should be fine to invert. To invert the softmax operation there. But no, I have to look. Yeah, we'll have to look into more detail. I'm just wondering if we classify. Yeah, that's right. I mean, we classified the end, so yeah, but I mean, one of the problems has been the max pooling operations, which are typically not invertible because you throw away information. But the soft max, there may be, yeah, if you do one-hot encoding, it should be, but I have to look into that in more detail. I mean, one of the problems have been the max pooling operations, but there are also ways around it. When you pool it, then you can what you get rid on the image dimension, you can just add on the feature dimension. This way, you can still keep it invertible. So there are, I mean, no, softmax is not a problem. I mean, there are papers which have shown that you can get nearly the same MNIST with invertible network, get nearly the same MNIST results with invertible neural networks. It's like tiny bit worse on this one. As I said, on these invertible networks, we're currently also exploring soft networks where you just have a soft constraint, but the network has no constraints on being directly invertible, and that also works nearly as well. So there are different working around. Also, I mean, it's certainly a bit awkward to have it by construction invertible, but it's a very stable learning now we have, and very a stable solution. But we look at other networks.
So thanks for the nice talk. I was wondering if you could say a bit more about the challenges of supervised learning generally for, let's say, applications where the data set is quite small, because I think some of the stuff you discussed relies also on having thousands and thousands of data points. And one of the big challenges is actually getting enough reliable data in the first place. And, and so could you say a little bit more about that?
I mean, first of all, you need data and then you need labels, right? What particular application you have in mind?
I mean, very often, for example, in biomolecular sciences, for example, one is looking for, strengths of binders or how fast various, I think you even mentioned drug design in your talk. And,
we just had a meeting with somebody.
Yeah, so things like, how fast drugs can bind on and off various targets. And usually that data is not as available as, other kinds of data. And so trying to infer what features of a very large, let's say, chemical space are relevant to influence such things is quite challenging.
Yeah. So so first of all, you don't get much data in general, right? It's not the labeling is not the problem, but the data in general is the problem. Yeah. I mean, with these people, we started to drift into experimental design discussion. So so certainly there are limits. I mean, you have little data. There are the shallower your networks are, right? It's all about generalization performance. You have to be the less data, you have to be more and more careful. And if you have very little data, you start to go towards Bayesian approach, where you just be super careful and want to get all of these uncertainties, not to miss anything in the network. So I've been also in the past in Dresden we had with the some department, I can't remember exactly what around drug design. They had so little data. They did random forest at this point, and I said this is like a kill of this, because this is when you've got a lot of data, and these networks as well. There's a lot of data. So exactly. So I would say little data, go to very shallow networks, or even some Bayesian approaches where you model everything in detail. But with these people, with the drug design, we drifted into experimental design to say, because with invertible neural networks, you get uncertainties out. So this would also be interesting for little data to see what distributions you get out. And then with the distributions, you can say what questions you may know more about what are the next questions to ask, for instance. How does your distribution space? So this is kind of what is quite interesting with experimental design. Also with the medical team, we also drift into the camera design to see how do you tune it in order to get unique answers and to get the same quality of answers. So I think that's quite interesting for us. On these rather practical things, we've been yeah, apart from the simulation where we also be very competitive, there's a huge community which does supervised learning and a lot of data and dealing with these practical things. We're not doing in our team so much with it. Yeah, I mean, currently there's so many people in machine learning, computer vision, that you kind of focus more on certain topics. And yeah, but I know these are the practical things. Yeah.
Great, thank you.
Mm-hmm.
Yep. Maybe also in addition to that question, actually, how you can visualize these features, not just for convolutional neural networks, but more broadly speaking, also for other types of neural networks. I mean, there, of course, you have these filter masks that you can like visualize and see what the network learns. But if you, for example, go for networks that generate or try to analyze more complex structures, also protein structures, something like that, then you run into problems with the actual visualization and what your network learns.
Yeah. I mean, there's a range of techniques. I only showed one or two examples here. I wanted to add one more, which is quite nice with this Husky example. So a lot of people also construct from the image what it has looked at, for instance, and why did it make certain decisions. So you can look at the input vector and see what has been what were the main parts of the input vector to come to this particular decision. I probably can show you a bit later, but there's a nice example where you see, okay, it used a wrong context, for instance. So you can look at the network, or you can look at images and try to like on the input and say what has been the relevant pixel, for instance, images which caused this decision. And there's a nice example with where you have two different breeds of dog, and the network is really good at doing this. But then you say what has been the decision for a particular image, and it only looked at the background. Basically, has learned that huskies are typically in snow background, and so it has basically not learned the husky, but it has learned the around and said when there's snow, it's a husky, right? I don't even know if there's a dog in there, so you can put a toaster, whatever, in there, and there's a snow background, and it says husky, right? But if you have if you never ask this question, and these kind of questions you can also ask the networks. I mean, there's a portfolio on methods on doing heat maps and so on to look at these networks. We mainly work with convolutional networks. I mean, some of the INN has been not convolutional, but apart from the INN, we in virtual network we do convolutional mainly.
So maybe I can just ask one quick question before we finish up. At the beginning, you mentioned that for image classification, the artificial neural networks are now better than humans. So we, of course, all have to fill out these captchas and do these. Should we now be making errors in order to be detected as human, or what are they doing? Those things?
Say again?
So should we be making errors to be detected as humans with those, or what's going on with what's behind, of course, what we as a user see? Yeah.
I mean, why do you why should you make?
Well, you pointed out for a capture.
Yeah. I understand.
Yeah, but if a neural network is so good, then it could imitate a human so good.
Yeah, exactly. So you have to get exactly. Yeah, exactly. Yeah. So you have to fit the right distribution, basically, right? So you have it as wrong as a human. As wrong as a human, yes.
Okay.
Yeah.
Constantly evolving tools then.
Yes.
Okay, I think we have to stop. We can continue the discussion over lunch. So let's just join me, please, and thank our speaker.